Okay, welcome back everyone to the second talk for the day. It's my great pleasure to introduce Dr. Imme Ebert-Uphoff. Dr. Imme Ebert-Uphoff has two positions at Colorado State University. She is a research professor in the Department of Electrical and Computer Engineering, and she is also the machine learning lead for CIRA, the Cooperative Institute for Research in the Atmosphere. She's worked in the area of data science applied to weather and climate for about a decade now, and she will teach us how to peer deeper into the black box. Thank you, Imme, for joining us, and over to you.
Thank you. I hope you can see my slides and hear me.
Yes, we can.
Okay, so welcome back to the second part of peering inside the black box of machine learning for earth science. So Amy made it much easier for me because I don't have to cover that many topics. I can focus just on a few topics because she already covered a whole range. So before I do anything else, I would like to acknowledge my wonderful collaborators on this topic: Kyle Hilburn, Yunjin Lee, Ben Toms, and Libby Barnes, who are all at Colorado State University. So first, before I jump into the real topic, I wanted to give some initial thoughts, maybe some philosophy. So what I found over the past few years is that gaining insights into a neural network is an iterative, scientist-driven discovery process. It's driven by old-fashioned methods of experimental design and hypothesis generation and testing, and the neural network visualization tools simply provide additional tools to assist this process, but they're not driving this process. And we'll see that in several examples. So just keep that in the back of your mind. All of those visualization tools are just additional tools. I see that a little bit like, if you use a microscope in biology, the microscope doesn't give you the solutions, but it's an additional tool to figure something out, right? And it's a little bit the same thing with neural network visualization tools. They provide additional tools to look inside the black box of neural networks, but they're not providing the results themselves. You still have to have the earth scientist in the loop. So the earth scientist will always remain very crucial in the entire process, and you will see that in lots of examples. All right, just a few acronyms. Artificial neural network, I sometimes call it ANN, I sometimes call it NN, it's all the same thing. Same thing, we're going to be talking about heat maps and attribution maps. I use those interchangeably, and it really depends on which paper you read, whether they call them one thing or the other, but they're really the same in this context. And then lastly, I just wanted to share an acronym that's commonly used in computer science with you. If you hear XAI, it stands for explainable AI, which is just a common term used to describe the whole area of neural network or machine learning interpretation and visualization. And Amy already covered a lot of visualization methods for other machine learning methods. I will mainly be focusing on neural networks. So what will I cover? I'm planning to cover two different methods that Amy didn't cover, which are number one, layer-wise relevance propagation, and number two, receptive fields of convolutional neural networks. So layer-wise relevance propagation is really a method for identifying strategies that the neural network uses by looking at the decision process for specific samples. And receptive fields, on the other hand, are a property of the neural network architecture, which is very helpful, in my opinion, for neural network architecture selection interpretation. I will spend at least 2/3 of my talk on topic number one. And if there are lots of questions, I'd rather go slowly and make sure everybody gets topic number one. So if we don't get into topic number two, the slides are pretty self-explanatory and they're posted, so you can always look at that, but I'm hoping to get to both topics. So let's get started with number one. So again, the motivation, you've heard some of this from Amy. Why do we care about these visualization methods? So neural networks have emerged clearly as promising tools in countless earth science-related applications, otherwise all of you wouldn't be here today. They perform amazingly well at many complex tasks, and they're generally treated as a black box. It's usually considered too difficult a task to understand how they work. So why is that a problem? If they're working fine, why do we care how they work? Why don't we just leave them alone and say they're doing their job, so let's just not worry? Well, to motivate that, I'm going to use some examples from this paper, which is shown in red over here. And this paper deals with using a neural network trained for object recognition and images. And then they're going to look at how does the neural network decide whether there's a horse in a given image. And the methodology used in that paper is step one is you train a neural network to decide whether there's a horse. And then you apply visualization techniques, in our case LRP, to analyze the network strategies. And again, LRP stands for layer-wise relevance propagation, and that method was actually invented by this group over here. So the following slides provide two different things. Number one, it provides an example of problematic strategies that a neural network might use, but it also shows you a way to identify such strategies. So you see the visualization tools in action. So let's look at this. Let's say you train your neural network and it's trained to detect horses. And now we're looking at two images at the top over here that the neural network has decided contain horses. At the bottom, what you see is what we call a heat map or attribution map. So this one belongs to this one, and that one belongs to this one. So what you see is basically an overlay. You can take this image here and put it on top of this one, and it will tell you where was the neural network looking when it decided that there are horses here. So if you look at the bottom over here, you see those red spots. So the red spots pretty much correspond with the three horses over here, these big red spots. And those pixels in the input image make it more likely, they increase the confidence that the neural network thinks there's a horse. The blue areas decrease the confidence, and the black areas are deemed not relevant. So again, always when you see a heat map like this, mentally overlay it with the input image. And again, it tells you where was the neural network looking when it made the decision. That's when you use LRP. That's the interpretation that these heat maps have. Okay, so let's answer the question. What does the neural network detect in these images? It detects a horse, but where was it looking? Well, I was mainly looking at horse parts because the red areas actually line up with horse parts. It doesn't get it perfectly, you know, there are parts here that are marked blue, should have been red, but it mostly is looking at this. So that seems pretty reasonable. Let's look at this case. So you see two images at the top, and you see in the heat maps down here where the neural network was looking when it decided that there's a horse in this image. What do you notice? What is it looking at? Well, this red area here at the bottom lines up with the poles, barely with the horses. So what the neural network really is doing here is it's detecting the poles, and it's learned that in the set of images that it was given, that whenever there were poles, there was a horse. So now it thinks whenever there are poles, there must be a horse. And that's clearly not a great strategy, because if you ever come across an image that contains poles but no horse, poles of this sort, you get a false positive because the neural network is going to say, I see poles, so there must be a horse. So it's really not a great strategy. It's called a false positive, or I guess people would also call it a false alarm. It's not what we want, not a good strategy. The third strategy that the authors found was looking at this image. So in this image, again, the neural network said, I see that there's a horse in this image. But when they asked, where were you looking when you decided that? This is where it was looking. Look at this. It's not looking at the horse at all. It's looking at the bottom left. What's in the bottom left? It's a watermark. It's actually turned out that about 1/3 of all the images in their database that had horses contained this little copyright notice and HTML tag, because that came with that database. So is this a good strategy? Definitely not, because in the real world, there aren't going to be HTML tags. And so most likely, if you take those tags, it might be that the neural network then would say, there's no horse in this image because I don't see this tag, because it learned to focus too much on this tag. So that would result in many false negatives, also known as misses. So what happened here? Don't blame the algorithm, because it did exactly what it was supposed to. The algorithm was given images and labels, and it was supposed to use any information it could to learn how to make the best decisions. So the algorithm correctly learned correlations present in the data to achieve its objective. The problem was really that some of the correlations that were in the images were not representative of correlation in the real world. For example, in the real world, these poles can occur without a horse, and there are no HTML tags in the real world. And we can call this the inadvertent correlation present only in the data problem. And the algorithm then seems to perform well, but its reasoning does not generalize to the world. So the conclusion is, you have to be careful. If we want to use these things, not for Netflix movie recommendations, but for telling people whether they need to evacuate because there's a hurricane coming, we need to make sure we don't use any wrong strategies. So that's just a cautionary note that you can learn this incorrect correlations. And that's another reason why it's really important to look at the strategies that your neural network is using. And of course, to make sure that your data set is representative of the real world as much as it can. But we also learned that the visualization method, in this case LRP, proved to be really useful to detect the correct and incorrect strategies. And of course, the next question is, how can we use those same tools for earth science applications? And just even if this wasn't enough motivation, there are just 3 primary reasons that I see for using these visualization tools. Number 1, you get increased trust in your network, because if you learn the strategies, the more you know about your method, the more likely you are to use it. You're just comfortable because you actually know what it does underneath. Secondly, important information is there for the design of neural networks, and you can even enable physics-guided machine learning. And that brings up, by the way, the point that I mentioned. We are going to have a workshop on physics-guided machine learning, and I put the link to the homepage where that will be announced in the Slido deck, so you should see it there. It also can provide a new role for machine learning. If you first train a neural network to recognize patterns, and then you're able to extract those patterns, you can actually discover new science. And I only have one slide of that, but we will get back to this later. So I distinguish 2 different visualization tools, and we're just talking about visualization tools right now for neural networks. So shown here is just one simple, plain, vanilla neural network, fully connected, but it could also be convolutional neural network. So type A tries to understand all, or at least some of the internal components of your neural network. So if you look at your neural network, on the left side, you have your input layer, all the yellow nodes, and you know exactly what each of those neurons corresponds to, because that's your input that you're giving, and you know exactly what you're giving it. The same thing is true for the output. It could be one node, it could be many nodes, but you pretty much know what every neuron over here corresponds to. That is usually not true for all the nodes that are in between. Those are called the hidden nodes because you don't really know their meaning. And what these type A feature visualization methods do is that they're trying to figure out what one or more of those neurons, specific neurons, mean. What is the physical or otherwise meaning of those specific neurons? So you're trying to get into the internal components of your neural network. And I will just mention 2 different methods. I won't go into this too much because we'll deal more with type B, which I will get to in a second. So if you're trying to visualize the meaning of individual neurons, 2 very common methods are method number 1. You identify all the training samples that yield high activation of a specific neuron. So you pick a neuron, and then you just look at all the different samples, input samples that you had, and you just check how much does each sample activate that specific neuron when you feed it to the neural network. And then you just select the ones, you just run it through, and you pick, so say, 10 images that gave you maximal activation of that neuron. And a wonderful example of that is this paper down here, which is also a wonderful example of transfer learning. So I highly recommend this paper by the Stanford group. Method number 2 is to generate synthetic images that maximize the activation of a specific neuron. And you heard a little bit about that already from Amy. And so a great paper that discusses that for atmospheric science applications is Amy's paper over here. And in fact, this paper is a great summary of everything that Amy was talking about in her previous talk. So if you want to know anything about what she talked about in more detail, go and read this paper. It's generally known as the BAMS paper for explainable AI. So this is a great paper. If you only read one paper, go read this one. All right. The reason why these type A methods are very, very popular in computer science, but not so much in earth sciences, is the following. If you analyze cats and dogs, then you often have these nice edges, you have objects parts, you have eyes, ears, noses, all those kind of things. But if you look at atmospheric rivers and cold fronts, you usually have fuzzy boundaries. You have few distinct parts. You don't have body parts like eyes and ears and noses that you can easily pick up. So if you're trying to then analyze what does each neuron mean, what you're getting here is something that's a lot less distinct and a lot less obvious what it means. And that's one of the reasons why these things work so well for distinguishing cats and dogs and ships and all that stuff. But if you're dealing with atmospheric rivers and cold fronts, I kind of prefer type B, and that's what you see more commonly used. Type B being where you try to understand the whole neural network at once. So the whole idea for the type B, which are attribution or explaining decision methods, is that you try to understand the neural network's overall decision making for a specific input. So now, let's say you call your inputs over here, you call them X, and your output you call Y. You now look at your neural network of just being a function that maps your X to your Y. So Y equals f of X. And you just try to understand the overall function rather than trying to get at the meaning of the individual neurons over here. So again, you seek to understand the reasoning of the entire neural network algorithm for a specific input, and you do not worry about the meaning of the intermediate nodes. Okay. So a very common means of explanation is these heat maps, which Amy already showed in her talk. And I just want to walk you through one more example over here. So in this case, you have a neural network that was trained to understand or to recognize different kind of animals, including lots of fish and sharks and whatnot. And so here you feed in the image of a shark, you feed into your machine learning black box that you're hoping to make more transparent. So you're trying to take the blackness out of it. The neural network decides, I think this is a shark, but now you're trying to ask it, you're saying, okay, but why do you think it is a shark? And one way of answering that question is to try to ask the neural network for an explanation in terms of a heat map. And the heat map, again, if you use LRP, tells you where was the neural network paying attention to in the input image when it decided that this image contains a shark. So you see over here, it's mainly the outline that it pays attention to, and then this particular fin makes it very different from other sea animals, and so this one stands out in particular. So again, the heat maps indicate in this case the region and input sample that are key for the decision or estimate made by the neural network for this input. So first of all, the visualization toolbox is available. You don't have to code this all up by yourself. The heat maps can be calculated with many different algorithms, and Amy already talked about saliency maps and GradCam this morning. And there are other ones like occlusion sensitivities, and my favorite one, layer-wise relevance propagation, which we'll talk about more. And new methods are being developed as we speak. I'm sure the question is going to come up, which method is the best one? Well, there is no single best one. Each method has its pros and cons. And in particular, not every method works for every neural network architecture. For example, if you take GradCam, that works wonderfully if you have a classification problem. But if you have an if you don't have a dense layer on your neural network, say you have an image-to-image sensation problem, GradCam just doesn't work. It's not designed for that. So different methods have different ranges of architectures that they can deal with, and specifically, they answer different questions. And we will see one example where I compare layer-wise relevance propagation with saliency maps, and you see a little bit what the differences in the output. Just to be perfectly clear, I do not want to promote LRP as the best method. It's just that it worked well for many of our applications, so I'm using it for examples, and just the idea is to show what visualization methods in general can do for the community, and I'm just using LRP as an example. And we use images here as input for illustration, but it doesn't have to be an input image. You could have other things as well. So as I said, you don't have to code this up yourself. There are visualization toolboxes. Package number one, I would suggest, is the investigate package. And if you're wondering about the grammar in this word, that's when you have them. If you take neural network and you stick that into investigate, then you get the investigate with a double capital N. Here's where you can download it. It's all free. It's open source. There's a PyTorch implementation. There's the TF Keras implementation, the TF, so TensorFlow implementation. It does not support 2.0 yet, but there's a new version coming soon. And the investigate package includes LRP methods because it was written by the people who developed LRP. So you see some LRP methods on the left, on the right over here, and a bunch of other methods over here. Another package that I like very much is TF Explain. It doesn't have LRP, but it has lots of other things. It has GradCam, occlusion sensitivity, and smooth grad. So there are lots of other toolboxes out there. I will explain in the next 2 to 3 slides the basics of LRP a little, and then I will take a break for questions. So how does layer-wise relevance propagation work? Just a very basic overview. Let's say you have your neural network here. So you're feeding in your input, and this is again shown as a fully connected neural network, but it could be convolutional one as well. So you feed in, say, an image over here, and out comes, say, some number, say a classification or something. So how it works is that you feed in your input sample, and you do a regular forward pass of the neural network that calculates the output, but it also calculates all of the activations over here. So now for each neuron, you know the activation of that neuron based on that image. So then what you do is that you do a new backward pass that propagates the concept of relevance backwards. So what happens is you take the output over here, you stick it in here and say, that's the relevance value for this neuron. And now you try to calculate the relevance of every single neuron going backwards. And the way you do that is you look at the activation and the weights, because you know the activations from the forward pass, you know how active each neuron is for this image, how strongly it was activated. You also know all the weights. So you can now go ahead and say, okay, this value over here, where did that come from in the forward pass? What was the strongest activating neuron that also had a strong weight? And you, based on percentages of the ratio of how strongly these are activated and how strongly they're being propagated to the weights, you take the value over here and you assign it to those ones proportional to how important they were to pass the value forward. And then you do the same thing from this one to that one. You basically take this neuron and you figure out the value over here, which neurons were most responsible for triggering it because the weights were strong and because the activation was strong. And again, you don't just take the maximum one, you basically take it percentage-wise. You say, okay, the relevance of this one came from the relevance of those three. You redistribute it this way with this redistribution rule, and you continue doing that until you get to the input image. And once you get to the input image, you basically have your heat map. You basically have a relevance of every single pixel that tells you, it's an approximation, but it tells you an approximation how important each of those pixels were to come up with this final number. And again, this is not your usual backpropagation pass. This is a newly defined rule, which I will just show on the next slide, which depends again on the weights and the activation of the different neurons, and then just calculates backwards what the relevant is of the relevance contribution of one neuron is given the neuron in the higher layer. And so for all the details, look over here. So before I go into examples, I just wanted to make 3 statements. We have found LRP to be extremely useful for many of our applications. If you want to look for how-to tips, look for this paper, and the full citation is in the references at the very end. But the biggest limitation of LRP is that so far it's only available for simple neural network architectures, but extensions are being developed as we speak. The theory is actually fairly general, but the implementations right now are fairly limited, and that's probably one of the reasons why we don't see LRP that much. But if you choose an architecture like a densely connected network or a simple convolutional neural network without skip layers, you can use LRP. Okay, before I go into applications, let me take some questions. So let's see what we have here in questions. Okay, so John asks, let me see here. So the first one is just my plug for the workshop. If you click on this website, you see on the left side a menu at the very bottom, it says workshop. So far it only says it will be from August 18th to 20th, but there will be more details coming soon, probably next week. Then John asked how to physically interpret, compare LRP heat map values magnitudes. Use them as weights to inputs, normalize them somehow. I think what you're asking is, so you get your heat map, what do you do with it, right? How do you interpret them? And that's going to be, I think, much more clear once I go through the application. So if maybe you keep your question there, and if my explanation there isn't clear, we can just go over that question, because I'm hoping that will be answered. Which method do you recommend for regression problems? Okay, so that's a good one. So LRP, if you take it just off, it's designed for classification. We do use it off the label for regression. So you can use LRP also for regression problems, but you have to be a little careful because your output numbers are actually interpreted as probabilities. So if you go below 0, you have a problem. If you look at the second paper in the reference list at the very end, that goes into that more deeply. But I would say more generally, I love LRP, but really which method is best? Again, I will follow Amy's lead and say, try several and see what you learn from them. Try if you have a regular, let's see, regression problem. You could use LRP, you could use Saliency, you could not use GradCam. So maybe smooth grad. I would just try several of those and see which ones work, which one tell you the most. Okay, if different interpretability masses don't rank the same features as important, what is the appropriate conclusion next step? we actually, as you will see in a second, and maybe I should take more questions just after going through the applications, what you will see is that we don't do just feature ranking. We really are trying to learn about the strategies of the neural network. And so it's not that much a question of contradicting features that's important. It's really a question of the earth scientist trying to understand what all the different strategies are that the neural network is using. I hope that kind of answers the question. Is LRP akin to feature matching at every layer? I think it's quite different, especially if you think of a fully connected network, you don't even have features. So LRP really tries to track what the strongest flow of information is in your network, if you will, just saying that loosely, where the strongest connections and which pathways that triggered the most to the end. That's what it's trying to figure out, and going all the way back to the input image. Inadvertent correlation present only in data could be translated as an input data problem. It's a training step. That is definitely true. I mean, in their case, definitely they made lots of mistakes, but you'd be surprised how often these kind of things pop up. You know, I mean, it's even like where you take your data. You may have things like, oh, I want to figure out whether there's an airplane, and you always take images only during the day. And so somehow the neural network learns, oh, only during certain daylight times is there going to be an airplane, or is there going to be certain things. So yes, it is true. It is a data problem, but it's a data problem that's really hard to avoid. It happens very, very easily that there are some correlations that you didn't think of that the neural network picks up on. Next question, when looking at relative importance of different pixels, can you look at the importance of different image bands individually? That sounds like by image bands, I assume you mean input channels, and yes, you can. And in fact, we'll show you an example of that in a second. And maybe that's the last question I take right now. Does peering into ML models depend on how well the model is built? Can it mislead us? So first of all, you want to keep your model as simple as possible. The more layers you have and the more complex your neural network model is, the harder it is to learn what it is doing. Can it mislead us? Again, you know, at the beginning, I said there's this whole, that the neural network tools are really just hypothesis generation. So you generate a hypothesis and you still have to go back and test it. So yes, the initial results can mislead you, that you think, oh, that's what the pattern means. But so you basically have to test it. So yes, it can mislead you. So you always have to do a hypothesis testing. And I think with some of those examples, that will become more clear. So I will go back now to the presentation, if you don't mind. So application 1 is driven by Yoonjin Lee, who is a PhD student with Chris Kumo here at CSU. And her project is to detect convection from satellite images. So just as a little bit of background, why is it important to detect convection? Convection releases heat. And if we can determine the locations of convection satellite images, we can feed that back in real time in our numerical weather prediction models, because they're not so good at figuring out where latent heat is being released. So if we can use our observations right now in the data assimilation task, and we can use our satellite observations to quickly detect where convection is, and then feed it back into our numerical weather prediction models, we could improve the predictions generated by our numerical weather prediction models. So just showing you an example here. This is a beautiful video stream where you can see convection happening in action. So everything that has like high brightness over here, and it kind of bubbles because convection is an upward motion. So you have all this bubbling motion here and here and here and here that humans can really spot very well in videos. We're not so good at spotting it in a single image, but they're pretty good at spotting it in videos because we see this bubbling motion. So what humans are looking for when they're trying to figure out where the convection is, again, we look for high brightness and we look for this bubbling texture. So again, humans look for high brightness and it's a bubbling. And so now we wanted to set up a neural network to figure this out. And we thought, well, if humans are better at figuring this out, if we have several images, a sequence, a video, we should give the neural networks the same chance. So we feed in a single sample, always a sequence of 5 images that are 2 minutes apart. So 0, 2, 4, 8, 10 minutes at the same location. And we just use a classic image classification network with only 2 output nodes. One is there is convection, the other one is there's no convection. So the method we use to analyze that then is that we train the neural network, then we freeze the neural network. So we leave the weights and the biases as they are, they're now fixed. We feed a specific input sample to our neural network, and then we apply an LRP analysis for the specific example, which tells us again which part or area of the input sample is important for this neural network output. All right, so what do we see? So for this example, it's just one sample where the neural network decided there is convection present in the sequence. So again, the output of the neural network is just, is in the sequence anywhere, is there convection present, yes or no? And so the neural network says, yes, there is convection present. So then we're asking, so where were you looking when you decided that there is convection? And so you see here, and maybe that answers the question from before, because you can feed this in as 5 different channels, although we use the 3D convolution, but you could see this as 5 channels. You can then see in the heat map for the 5 different channels where the neural network was looking. And if you turn this over again to our Earth scientist, Yun Jin in this case, she found by looking at enough samples and enough heat maps that this main strategies the neural network was using was, it was just looking at the brightness. But when there was high bubbling, it didn't care. It didn't look at that. So it only used one of our human strategies and it didn't use the other one. And it wasn't doing that well either. So what we learned from this was that we had to push our neural network to look more at texture things. And we use now tools like pre-training on samples that mainly have the texture signal and less of the brightness signal. And also we've reformulated the segmentation task to give the neural network more feedback on where to look during the training. But the key point of this slide is really just to demonstrate the process. And keep in mind what I said at the beginning. I said these visualization tools are just tools, but the Earth scientist is the one who's generating the hypothesis. Because we fed in this image, we got the heat map, but the heat map doesn't give me an explanation by itself. It's the Earth scientist who's then looking at those pairs of this and where the neural network was looking to say, oh, I see, the neural network was looking where it was bright, but it's not looking where the texture is. So it's again, the hypothesis generation comes from the Earth scientist. So again, the key part is just the visualization brings the neural network reasoning back to the space of physics and expert knowledge so that Yun Jin could actually look at it and say, oh, if this is where the neural network is looking, I think I know what it's doing, right? So it's really only a part of the ways of visualization, but then the important part is to use those tools then intelligently with the Earth scientists to come up with the strategies. All right, a second example, and a person driving this project is Kyle Hilburn. So the second application is, because I just showed you a classification architecture, now we're doing something with image-to-image sensation. So the application here is that we're trying to generate synthetic radar images from GOES imagery. So GOES is the Geostationary Satellite System. It stands for Geostationary Operations Environmental Satellite, in our case, GOES 16. And it gives you basically images all over CONUS, so the continental United States. So every few minutes, you can get those 4 channels that we picked. This is channel 7, 9, 13, and the lightning channel. GLM stands for Geostationary Lightning Mapper, which is on GOES 16. And so we can get those images everywhere over the continental United States. And that's going to be our input. Our output, what we're trying to emulate, is MRMS, which is multi-radar, multi-sensor estimation of radar images. So if you're not familiar with MRMS, it integrates data from multiple radar networks. It also integrates surface and satellite observation and NWP models. But the key thing is it gives you radar, but only where radar is available. And radar isn't available everywhere in the United States. So if you take mountain ranges, for example, you usually have no radar coverage. And we would love to have radar coverage everywhere. And the idea is we can generate ourselves an estimate of that just from the geostationary satellites that we have available everywhere. So again, the input is we take the geostationary satellites and we try to emulate MRMS everywhere in the United States where MRMS isn't available to observations. So again, it's an image sensation problem. You have your input image, you have your neural network, you have your output image. And so this is just the architecture we're using. We feed in our 4 different channels. Goes in here, classical encoder decoder layer. This is very much like what you saw in Jeb Stewart's segmentation problem, just that we don't have the skip layers. So you have your encoder and your decoder. Just imagine you have your UNet, you just take out the skip layers. You just have convolution, pooling, convolution, pooling, convolution, pooling to encode and extract features. And then you have your decoder layer with convolution upsampling, convolution upsampling, convolution upsampling, and one by one convolution that then gives you an output image. So again, it's an image to image translation. And so the question we were asking was, okay, we're getting some reasonable results over here, but how is it actually doing this? Well, the science question we asked is, how does the neural network know when to create, say, large MIMS estimates, large reflectivity values? So the method we used, and again, here's the Earth scientist who says, okay, let's design some experiments to see how the neural network is doing this. So we selected some examples where the MIMS estimates were high. In fact, we selected lots of them. And then we asked the neural network again, okay, why did you create large MIMS values there? Where was the neural network looking when it was doing that? So without going through too much detail over here, we basically found these are the different channels. So these are the 1, 2, 3, 4 input channel of course. So 3 different regular channels and the lightning channel. And this is what the output should be. And this is if we zoom in just to a small area, we just look at 1 pixel over here and we ask, where was the neural network looking when it generated this high value over here? And for this example, we find it was mainly looking at lightning. So it didn't care that much about those values. We find out that one strategy of the neural network is that lightning is the strongest trigger. Whenever there is much in the lightning channel at a pixel, it will create a high output. Okay, so that's a totally sufficient condition. Lightning is an extremely strong trigger. LRP told us that just by looking at examples like this. Then we took the same input sample and we just blocked out all the lightning and we checked where does the neural network look then? And we realized, oh, then it's looking in these places here. What are these places? Well, if you compare those to the gradient of the input image, you see, oh, it's just the gradient of the image and it's also the cloud boundary. So the strategy we found is that if no lightning is present, then the neural network focuses on locations with strong gradients in the other 3 channels, so the cloud boundaries. And in fact, by looking at more samples, we found that it looks at the large gradients, but it also looks at areas of extremely high brightness. So the third strategy we found was that extremely dense areas of clouds, as you can see kind of over here, so extremely dense areas of clouds also trigger high MIMS values. So we just went through lots of samples that triggered high MIMS values, and we always found the same 3 strategies. Number 1 was strong lightning. Number 2 was cloud boundaries and strong gradients of the cloud. And number 3 was extremely dense areas. So those were the 3 key strategies our neural network seems to be using when it decides how strong the MIMS reflectivity value should be chosen. We also tried a saliency method, which just takes a derivative. And it just always gives us the same result. It just always says, well, if you were to increase lighting in your images, then you would get more MIMS. So in other words, saliency only gave us the strongest strategy, number 1. It only told us that lightning is triggering high MIMS values, but it didn't give us the other 3 values, the other 3 strategies. But LRP did, and that's why we like LRP so much. All right. I just have 1 slide, and then we'll take a break for questions again. So this slide is just some references to the wonderful work initiated by Libby Barnes, who realized pretty early on that you could actually use neural networks to discover new science. And Ben Toms was actually the one who found LRP as a great tool for earth sciences. So if you want to check out more about this, so Ben Toms wrote this paper on physically interpretable neural networks for the geosciences, where he discusses how you can use LRP to discover new science. And here are 2 papers by Libby, which talk more about how you can use neural networks and then neural networks with LRP in the last paper to figure out, for example, indicator patterns of climate change. And the key idea here is that neural networks are just great at picking up and utilizing spatial patterns. And so if we ask the neural network, well, what are the spatial patterns you're finding, and we can extract those from there, we can actually discover some new science. And that's what this paper deals with. So if you're interested in that topic, feel free to look at any of those papers. With that, before we go to the next topic, I will take some questions. Okay. Let's see, Noah asked, is LRP a nonlinear analog of adjoint model? I have to admit that I don't know what an adjoint model is, so it's kind of hard for me to answer that question. So Nora, feel free to send me an email, and maybe if you explain to me what an adjoint model is, I could figure out whether it's similar to LRP. Okay, still not clear, John D says, still not clear about the physical meaning of the magnitude of LRP heat match for each input. Okay, so between different inputs. So let's go back to, say, this slide over here. These are actually, so if you take the different channels, I think what you're asking is, what's the relationship between all of those in terms of scaling? So you actually have to be a little careful with LRP that you normalize your different input channels in a consistent way. Because it will tell you again, it will tell you, given one pixel over here, it kind of redistributes it to those values. So if you add all of the red values over here, if you add them all up, if it was an approximation, it was perfect, it should give you exactly as result the value that you estimated at this pixel over here. So these ones all add up to the value over here. But that in order to interpret them, to really say, oh, okay, if I sum over all the values over here, which actually happens to be 0.1260, if you go by everything over here, is this really more important than this one, which gives me a sum of 0.2584? That is true only if you normalize the images to be kind of in the same range at the very beginning, the different channels. But if you normalize them, say, to have values between 0 and 1, and you have a similar distribution for all of them, then you can actually take that to say, okay, if the sum of all the pixels in this image is the largest, then this channel has the biggest importance, and you can really take those as the importance of them as really being objective. Okay, I hope that answers John's questions. Then there's a question, did you use time dimension for convective detection using satellites? So that goes back to this one. We actually have two different neural networks. One sets it up as a 3D convolution, which means in this case, yes, you have three axes, X and Y and time. And so then time is your third dimension. We didn't see much difference to just using that instead as 5 different channels. So if you set up in our second neural network, we set it up with 5 different channels, but not telling it that there's different time steps and just saying, okay, here are 5 different images, you go make sense of it, and I'm not telling you that they're 2 minutes apart. It wasn't that different. So you can do it either way. If you do a speedy convolution, you use it as a time dimension. If you use it as 5 different input channels, then you don't have it as time dimension, you use it as channels. And I would love for somebody to really dig into this and say what the difference is, but we haven't seen that much difference. Next question, how to include both texture and time information for satellite images? As you mentioned, both are important for convection detection. We are actually, let's see, both texture and time. I think the harder part of this question is how to incorporate texture. How do you push your neural network to really detect texture? And I don't think there's like a global answer for it. We're actually starting to explore a method that Karthik made us aware of, which is topological data analysis. And we're just starting to talk to Henry Adams in our math department here on how we can extract the texture information before we even feed the satellite image into the neural network. So that may be another one to look at. Can NLP provide information about the importance of the relationship between pixels or only the individual pixels? The relationships between pixels, I would say the answer is no. It doesn't tell you about the relationship between pixels. If 2 pixels are both important, they will pop up together. And in fact, if they have redundant information, it totally depends on the neural network, whether it picks one pixel over the other one. So that really depends on your, let's say, number one, no, LRP does not tell you about the relationship between the pixels. It just tells you such and such pixels are important, but it doesn't tell you about any relationships. Number two, again, if you have 2 pixels with redundant information, you can't guarantee which one your neural network will train on. It depends a lot on the random seed you're using and all that. I hope that answers that question a little. What approach from physics-based machine learning can be used in identifying stratiform convection, which is important for snowfall detection? Oh, that's a tough question. I don't think I'm the right expert to answer that question. That's probably a better question to be directed to true Earth scientists who really knows better about convection. So I'm afraid I don't know the answer to that question. But in terms of physics guided, I'm thinking again using texture. And there's actually a lot of papers on unsupervised learning to determine different types of clouds. That may be interesting. And if you send me an email, I can send you some reference to that. Can NLP be used for tracking a feature once detected in a satellite image? I hope so. In fact, that's one of those things we were thinking. Because if you keep on asking where are you looking, it should be able to do the location of the object. So I'm hoping that's possible, but I haven't tried it. That's an excellent idea. How do you distribute the relative relevance values to the individual neurons? I think what you're asking is how does LRP figure this out? And I will point you again to the Montalban paper and also to this slide over here. So really, this is the method over here at the bottom, combined with this rule that figures out how to redistribute the relevance. And again, I will just give you, let's say you have 3 neurons, and let's say you're here, and this is highly triggered, and you have 3 different neurons in the previous layer. And this one had a really high activation, and it has a high weight. And this one had no activation, and it has a high weight. And this one has low activation, but a high weight. Those 2 just don't trigger this very much. Only the one that has a higher weight connection and also has a high activation is going to trigger this a lot. So this one is going to be the most relevant, and those 2 are going to be less relevant. So that's kind of the most intuitive way to look at it. You're just looking at basically in your formula, you're looking at the product of the weight times the activation, and you only take the positive part of that for the positive attribution. You stick it in here, and you compare to all the other neurons in the layer, and that gives you the relevance. But again, I refer you to these other papers here. I'll take one more question, because then I would like to go back and just very briefly cover relevance, because we don't have much time left. Cover receptor fields. Humans are making use of the time-dependent behavior of the images to identify bubbling. Why is the neural network not identifying that time-dependent behavior as key? The neural network will always focus on what it finds easiest first. And it depends very much on setting up the data set. And so again, as we said first, what we learned is if it doesn't focus on the bubbling, maybe we have to feed it specifically, design an input data set where the bubbling signature is really strong, but the other things are not so strong. And the neural network will always try to go for the strongest signals first, and brightness is the easiest to pick up, right? The bubbling is hard because the clouds also move, so you have to figure out over time how those changes are the changes between the values in this image and in this image because of advection, because the cloud moved, or is it because it's convecting? So finding this combined spatial temporal pattern is not easy for the neural network. So it's easy to miss. So that's why we're also thinking about topological data analysis to make it a little easier, a little bit more obvious for the neural network to figure out those kind of bubbling texture signals. But that's kind of an open question, how you push the neural networks the most to discover those textures. And I think we'll figure out much more over the coming year. And with that, I will go back to the presentation. Oops. Okay. And just in a few minutes, cover the field of receptor fields. So, and I will just give you the basic idea. So as you know, if you have a convolutional neural network, your first layer is just look at the individual pixels. Then your filters will be triggered by things like edges. And then you get things that are even more complex, that are combinations of these things. And these are combinations of these things. And so basically, the features that you can recognize while you're going through your neural network, while you get to deeper and deeper layers, the features become both bigger and more complex. And we said before, because of the fuzzy boundaries and all this stuff, it's really hard to visualize these things and learn much from them. So it's hard to really figure out the patterns, but we still can track the size very easily. So the question is, what is the size of the features we can recognize, and can we match them to meteorological features? And the answer is yes, we can. And the sizes are called receptor field. And if you just Google receptor field, you can find lots of papers on how to calculate them. So the basic idea is just, I want to show you this. I will just skip through to this slide in the interest of time. So this is again our neural network that we used for the synthetic radar imagery. where we put in geostationary satellite images, and out comes an emulated radar image. And what we wanted to know is, if this is my input image, so that's the entire image that I feed in, that's 256 by 256 pixels, in the individual layers here, how big a meteorological feature can I actually, how big a space in the input space can I actually visualize at the different layers? And so it turns out at the end of the first convolution layer, it's tiny, you know. This is the area in the input image you can see. And it doesn't have to be the center, it can be anywhere, but just to give you an idea, this is how much context you can take in, how big a feature you can recognize. And as you go deeper and deeper, you see by the time you come out of the encoder layer, it's gotten much bigger. So now you have an area here where you can actually get a little bit of cloud texture. But this is the maximum feature size that you can, that the neural network can interpret when it comes out of this layer. And it keeps going, and at the end, you get to this size over here. So why is this important? Because if you think, based on your expert knowledge, that the neural network needs to know like a certain size of meteorological feature to make sense of the input image, to interpret it correctly, you better make sure that you design your neural network such that the receptor field, which is this red box over here, is big enough to actually capture this. All right. So again, I will emphasize that here. Always make sure your theoretical receptor field, which is your red box over here, is big enough to capture the meteorological features that you think are important for the neural network to understand. Because if you choose this to be too small, well, then your neural network just has no chance of actually capturing these things. And coming back to the question of texture, again, texture in our case with convection is really a tempospatial pattern. So you have to make sure your receptor field, if you're going in 3 dimensions, X, Y, and time, captures everything in space and time, that your time window is also big enough for your convolution to actually capture the texture that you want to have. Just very briefly, one of my last few slides, we just talked about a receptor field if you have no dense layers. So that's your typical image-to-image sensation setup. If you have an image classification task, you usually have dense layers at the end to give you a single output label. So usually the feature extraction block is pretty much the same as your encoder block, but then the features that come out of here, you have to interpret with your dense layers. And so in this case, you just calculate the receptor field up to here. And this will basically tell you what were the biggest features that you extracted before you went into then interpreting those features to come up with your output label, right? Because this part just interprets the features that were found up to here to then say, oh, okay, those features, this was a cat ear and a cat eye and all this, so I think it's a cat. It's just interpretation part. You can still apply receptor field here. Once you get over here, once you have your first dense layer, well, your receptor field is the entire space, the entire input space, so it's not particularly meaningful, but up to here is meaningful. So do use that even if you have a classification task, you can still use the receptor field to analyze the feature size up to here. Final thoughts, this should look familiar to you because it's exactly the same as my initial thoughts. Keep in mind, gaining insight into a neural network is an iterative, science-driven discovery process. It's driven by old-fashioned methods of experimental design, hypothesis generation, and testing, because you saw, again, the neural network visualization tools didn't give you the explanation. The earth scientist gave the explanation after designing experiments, and then after looking at the results, the visualization plots. So again, the neural network visualization tools simply provide additional tools to assist this process. It's like a microscope for a biologist. It doesn't do the science for you, but it lets you look at things that otherwise you wouldn't see. So the earth science always remains crucial in the entire process. How much can you get? Well, I like to compare to scanning a backpack through an X-ray scanner. You put in your backpack over here, you put it in your X-ray scanner, you get an inside view. You don't see everything, but you certainly see a lot more than you did at the beginning. I kind of look at it similarly with the machine learning tool. So you have your neural networks, which first you look at as a black box. You take your neural network, you stick it into your visualization toolbox, and then you get a more transparent view, kind of more like this up here. You see a lot of the things inside. You're never going to see every single little detail, but you see a lot more than you did at the beginning. So that's how I see visualization tools. And with that, I will just say that the remaining slides that will be posted have a bunch of toolboxes over here. If you want to read This first paper, again, is Amy's paper. It's really great. It's the paper to read for XAI, so go read this paper. That really covers a lot of her talk. And then most of what was covered in my talk is in the first paper over here. So feel free to look at this one. And with that, I will turn it back to questions. And there are several more slides where there are more references and reading material, recommended material by topic. So with that, let's go to the questions. Okay. First question, how do you distribute the relative relevance values to the neurons? I hope I covered this by now, because again, we looked at those different heat maps, and that really the relevance goes into, if you were to take all the different channels and all the pixels in there, once you normalize your channels properly before, you can really look at that and ask across all channels, which pixel and which channel was most important, etc. So it's really a ranking. Is a layer-based relevance propagation technique able to solve real-world problems? It's a tool. Is a microscope able to solve real biology problems? It's a tool, and it depends on what you do with it. So I think in our case, especially for emulating synthetic radar images, LRP really helped us to figure out the strategies. Because we were surprised, we were just wondering, how did the neural network figure this out? How do we come out with the estimate? But I will tell you that we don't use just LRP. Just as Amy was saying before, use a range of tools. So we also came up with synthetic experiments where we actually created synthetic inputs, different scenarios, send it to the neural network and see what does it do. So the second paper in the reference list, the paper by Kyle Hilbert and myself, actually goes in a lot of details of a whole range of methods you can use over there. If MIMS labels are not available in mountain regions, how do you make sure that the model does not detect snow or glaciers as convection? That is an excellent question, and we haven't gotten there yet. We are right now mainly testing it in regions where we actually do have ground truths. And it's exactly one of those things where the earth sciences are so important, because you just generate a hypothesis. You just basically told me, well, okay, your model may just really mess up for snow and glaciers. So the next thing is to set up either synthetic experiments or synthetic inputs, or just some kind of experiments that test it and see what the neural network does with that. So yes, that's the whole thing. If you go in a different regime, how do you test it? You really have to carefully come up with ideas of what you think can go wrong and test them, unfortunately. Okay, is it important to make sure your receptor field is not substantially larger than your feature of interest? So if you look at the slides, a lot of the slides that I skipped, you will see that we're kind of representing the receptor field as a box, but it turns out the influence of the pixels in the box is actually not equal everywhere. It's actually more like a Gaussian distribution, where the center of it, the center is much more important than the outside. So the first part of my answer is, you always want to make sure that your receptor field is a little bigger than what you want to have, because the neural network tends to focus more on the middle. But if you go way overboard, you're just wasting resources. You basically have a neural network that's way too deep. But the easiest way to figure this out is usually, you come up with kind of an initial guess of what you think your receptor field should be, and you design the depths of your architecture based on that. But then you go ahead and you do experiments with different depths. You go up, you add another 2 layers, or you take 2 layers out and you see how well your model works. And again, just as Amy said, I can't say it often enough, keep it simple. The simplest model that solves your task reasonably well is probably the best model you want to have, because you can understand it much better. So when we have a neural network that works pretty well, we always try to make it simple and see whether it still works well. Eliminate a layer or 2. See whether it still works well. And if it still works well, then use that one. So that kind of covers the question of, if you have a very large receptor field, go ahead and try whether a smaller one will do. How do you determine the sizes of features needed when you don't know what the object size will be? For example, not knowing how big a horse will be. So with the horse, you don't know where your camera is going to be. So you don't know how big the horse is going to be. In the application that I'm dealing with, I know where my geostationary satellite is, and I know how big a hurricane usually is. So in my examples, I'm lucky enough to know how big the meteorological feature size should be in the images that I'm getting. I'm trying to think of meteorological examples where you don't know that. But I think in most examples, you know the meteorological size of the feature, and you usually know where your instruments are. So I would say in most cases, you probably have a good idea. How do you decide convolution size and depth for methodological problems? If you could just go back to that one, the convolution size. So convolution size, so practically most, and I think Karthik is telling me, how much time do I have left for questions? Are we done?
About a minute or two.
Okay, so the convolution size. The most common one is 3 by 3. At the very beginning, when people were using neural networks, they were saying, oh, we want to have bigger features, so we're going to use the 7 by 7 or 9 by 9 or 11 by 11 convolution size. But it turned out that that's extremely inefficient because the number of families you have to learn goes up as squared. And so it's much better to have several layers that are only 3 by 3 rather than one layer that's 7 by 7. So usually the convolution size is 3 by 3 for most standard networks. The depths, again, a lot of it, unfortunately, is trial and error. You start out with a small one, you see how well it does, you make it a little bigger, you see how well it does. Again, you can use the receptor field kind of as an initial guess, but that's about it. Are these examples of unsupervised learning? Supervised, what is ground truth? I think so you're probably talking about the 3 different examples, the 3 different applications we had. Application 1 was a synthetic radar. It's definitely supervised because we have our ground truth, that's MIMS where it's available. Application 2 was the convection. That's actually a tricky one because you don't have ground truth. So we start out using heuristics that Yunjin had developed. So I would say generally pretty much everything I covered is supervised. Okay, so maybe one more question. What is pre-training? Sure. Okay. What is is there any way to tell the network what criteria they should consider to classify an image, since we already know how they work? So the loss function is clearly the biggest one, right? So you can weigh it differently depending on whether you have a class imbalance. You can think of lots of different ways. And that's actually, the loss function is the one thing that's usually not considered enough. Lots of people use IMSE at the beginning because that's a classic one that computer scientists use. You as an earth scientist are in a much better position to figure out what is it that I would care about, and then really take the time to formulate the loss function in that way. And I think with that, unfortunately, we'll have to wrap it up, but we can continue the panel discussion. Thank you.
Thank you very much, Imme, for a really nice talk on interpretation and various tools to explore and understand what these neural networks are doing. We'll have the afternoon panel session for a lot more questions, so please do continue thinking about this topic and post your questions on Slido. We'll take a short break for about 8 minutes and then be back at 20 minutes past the hour with Mike Pritchard for the next talk. Thank you very much.